I posted the key to the quiz 1. There's 2 versions, A and B. You check them out. They're on the Canvas site, of course. There's like a special section that I created, which was called Quiz and Exam Materials. Okay, so it's one of the first tabs that you see. It's right under, I think, first syllabus, lectures, and then quiz materials. So go there, check it out. The key is right there. We're almost done with grading the thing, so hopefully we can release the grades maybe later today. It'd be great. And then you can, feel good or bad about yourself. I don't know. Okay, so we will be moving on. Meanwhile, okay, train continues to our final destination, and we have already passed a few milestones. One of them is actually that last lecture, we finally looked at the wave function of the hydrogen atom. Okay, and that makes me very happy. Very happy. It was a great result, and so today we are going to investigate or explore what does it all mean, what does the wave function tell us, and how can we get to some atomic properties that we care about. So let's do that. So what we've done last time is we found expressions of the hydrogen wave function, and it looked like so. Wave function is psi, it has 3 quantum numbers, n, l, and ml. And it has 2 parts, namely r and y. R describes behavior along the radial coordinate, and the y describes the spherical part. Okay, together, of course, they trace out the full 3 dimensions of the atom. I cannot stress enough that this function is a function that describes the whereabouts or the characteristics of the electron. These are called electron wave functions. Okay, so this wave function can help us understand where the electron is and what its properties are. And that is going to be key for us to understand atomic properties in general. Chemistry is driven by electrons. Okay? So that's why we have to know what the electrons are doing. Now, what is one of the characteristics of this wave function? It is a solution of the Schrödinger equation. It forms a complete set, and like any complete set, the functions of this set are orthonormal. Orthonormal. Orthonormal means that they are orthogonal to one another, and the overlap integral of the function with itself equals 1. That's basically spelled out here. It looks like a lot, but really what it is just a function multiplied by another function from the set, integrated over my 3 dimensions. That's what it is. And it says that that integral is only 1 if n, l, and ml of those 2 functions all are the same. If one of them is different, it's 0. Okay, that's what it says. That's what these delta functions says. N must equal m prime, L must equal L prime, and ML must equal ML prime. If any of these is not true, the whole thing will be 0. AKA, any function in the set, any function that you pick, and you pair it with another one, that overlap integral is going to be 0. That means this is an orthonormal set. They're normalized to themselves, and the overlap with any other function from the set is 0. You see that the integration is over 3 coordinates. R runs from 0 to infinity, phi from 0 to 2 pi, and theta from 0 to pi. Okay? That's what dV says. dV is the volume element in spherical coordinates. How can I think about that? Well, something like this. You don't have to reproduce this. I'm just going to show it to you so you can maybe just appreciate it. You don't have to be able to draw this by heart. That's not the point. But you can see that a volume element on a sphere is not a cube. Okay? If you have Cartesian coordinates, then my volume element dV is dx, dy, dz, which is kind of like a cube. But on the sphere, it's not. On the sphere, it's kind of like a contorted little shape. It's curved, okay, along theta. It also a little bit curved along phi. So if you see it's dr, then r d phi and r sine phi d theta if you trace out this volume element. It's a funny one, but this is how it looks. And therefore, my volume element is written, as we have already before, in the following way. The volume element, because it's the sphere, is looking like this. It's dv equals r squared sine theta dr d theta d phi. Okay? You may have seen this before in some kind of, I don't know, calculus class or physics class. And it's also true here, okay? Can't change this. This is just how it is. The volume element on the sphere has this form. So, if I would like to do the following, if I take my wave function, now remember, the wave function squared, or the modulus squared of the wave function, is its probability density. If I multiply the probability density with dV, density times volume is basically cancels out, so it's a probability. So this thing here is the probability of finding my electron in the volume element dV. Now what I'm going to do now, something interesting. I would like to find out where is the electron along the radial coordinate. What is the probability of finding the electron along the radial coordinate? And in order to do that, I'm taking this expression, but I'm integrating not over the entire volume, because that would mean, you know, that I'm integrating over the whole thing, which means 1, but I'm integrating only over the angular part, not over r. That's what this thing means. This omega means that I'm integrating out the angular coordinates, theta and phi, but I keep r. Okay, why would I do that? Because I would like to know where is it along r. I'm not interested in where is it along theta and phi. I'm basically collecting all theta and phi information, integrate it out, and only keep the dependence on r. That will be my radial probability. Okay? Where is my electron along the radial coordinate? That's what I would like to know. So that is basically the following. I'm going to take the function all the way on the top. I'm going to take the modulus square of it. Let's give it over here. R is a real function, so the modulus doesn't do anything. So I can just square it. And then I have the volume element that's written down here. But the integration is not over r, but only over theta and phi. What do I get? Well, good news for me and for you, really for all of us, is that this r doesn't depend on theta and phi. It only depends on r. This r too. So I'm going to take everything that just depends on r out of this integrand and keep only the things that depend on theta and phi, which is exactly what y does. Y is a function that depends on theta and phi, so that one is going to be integrated over all angular coordinates. The full sphere is going to be integrated out. Theta runs from 0 to pi, phi runs from 0 to 2 pi. That means I'm going to trace out the entire sphere. And you may recognize that this thing here is just the normalization condition for the spherical harmonics. If you integrate the spherical harmonics over all angular coordinates with itself, then you get 1, because it's a normalized function. Therefore, what I'm getting is this. Okay, so that function, big R squared times little r squared, I'm going to give a different name. I'm going to call it PR. And it's called the radial distribution function. It is the probability density, this guy, the probability density along the radial coordinate. This is what I would like to know. Okay? So this expression here tells me the probability of finding the electron along the radial coordinate at the position dr. The small section along r, dr, that section, what is the probability? That is the probability of finding the electron at that particular dr location. So this radial distribution function is very useful for me to study, to see how far is the electron away from the nucleus. What is the likelihood the electron is like at some distance from the nucleus? That has to do with the size of the atom. Okay? The farther the electron is away, the larger the atom is, right? Because it's defined by where its electrons are. So this radial distribution function is kind of an important parameter. It relates to an actual physical thing, namely the size of the atom, or the size of an orbital of the atom. So let's have a look at that. Let's consider, again, the simplest possible wave function for the electron in the atom, which is n equals 1, L equals 0, ML equals 0. That's the simplest one. It's the ground state of the electron in the hydrogen atom. That is the simplest possible, lowest energy wave function of the electron in the hydrogen atom. So, I would like to ask the question now, where is the electron at? Or what is the most probable radius of where this electron can be found? Okay, that's what I would like to know. Just to kind of visualize that, I'm going to first write out what this equation, what this wave function is. I know now what it looks like. I have an actual expression for this wave function, and it's here. There it is. The good news is, because this y00 is just a constant, and this r10 is simply a decaying exponential with a bunch of prefactors. Okay, you see that? And this is it. This is the wave function for the electron in the 1s orbital. Now I'm going to look at its probability density. That means I'm going to square this thing. Okay? And I'm going to visualize this. This is it. I'm going to plot this function. And now I'm going to do a hypothetical measurement, a hypothetical experiment. What is it? I'm going to take the atom and I'm going to pretend that I have a very sharp needle and I can just kind of do little measurements to see where is the electron at. What is the probability of finding the electron somewhere within this atom? And so every black dot is kind of a successful measurement. Okay? So where it is like more dense, that means there's a higher likelihood of finding the electron. The farther away, it becomes a little bit more sparse, lower. Now, I'm asking myself, what is the chance of finding it at a given radius? Okay? A given distance from the nucleus. I'm integrating out the angular coordinates. I'm going to say, what is the likelihood of finding it at a certain distance? So what I'm asking is, what is, let's say, the likelihood of finding the electron in one of these colorful rings? Okay? So I'm having colorful rings, and say, is it more likely to find the electron in, let's say, the outer ring, or is it more likely to find it in the inner ring? That's what I'm asking myself. Why would I ask myself that question? Because you may be able to see, well, it's in the middle. That's where it's like the most points. But actually, it's not that simple. Why not? Because even though it looks it's much sparser in the outer ring also traces a lot more area, okay, or more volume. So the outer ring has more volume, which means even though it's sparser, I'm integrating over a larger space, and therefore I can have more points. Okay, so we have to take care of the fact that if you move away from the center, that I'm actually tracing out larger volumes. And this is important. So, if I plot this function, if I'm just going to take this function, psi, 1, 0, 0, I'm going to square it, I'm going to trace it out, okay, I'm going to plot it along R, I get this, it's a decaying exponential. But that's not the probability of finding the electron at the given radius. Okay? This visualization is not that. Why not? Because of exactly this point. The point is, if I now integrate out the angular coordinates and keep R, this is what we just did on the previous slide, I have to actually look at the radial distribution function, not just the wave function squared. Okay? So I have to look at R squared big R squared, dr. This is the probability of finding the electron at a certain distance in this location, dr. And because the sphere becomes larger the farther you go away, namely the surface area of the sphere grows like 4 pi r squared, because that's the surface area of a sphere. So a small sphere has just a little tiny surface. A bigger sphere, farther away, bigger r, has a lot more surface, a lot more chances of finding the electron just by the virtue of being bigger. That's why this r squared needs to be there in its consideration. Okay? So if I look at this radial distribution function, this is really what it looks like. It's the multiplication of the wave function squared with the r squared in it. If you multiply that by that, you get this. Okay? You get this function. Because little r squared starts at 0, the tiniest little sphere is 0. And then I'm going to grow from there. And it gets bigger, bigger quadratically. So if you multiply the top with the middle figure, you get this result. Just a multiplication. And you can now see at those rings, that's why these colors are here, that actually it's most likely to be found in, let's say, this second ring that was shown here. Not the first, but the second, and then it kind of tails off. All right? So, what is the most probable location that you will find the electron at? It's not at the nucleus. In fact, at the nucleus, the chance is 0. Okay? The chance is 0 at the nucleus. It's away from the nucleus at this location that you're most likely to find the electron. Farther away, of course, it goes to 0, as it must, because you will not find the electron there. Okay, so keep that figure in mind. What I'd like to do now is I would like to calculate what is that point, the top of this figure. Go up, that top, and go down. Where is that thing at? What is the location? The most probable radius of the electron. Can I compute that? Can I predict, with the theory that we have, the exact location? Or exact location, but the most probable radius, aka the size of the hydrogen atom. Can I predict the size of the hydrogen atom with this theory or not? So what I have to do is I take this radial distribution function and determine where does it top out? Well, if you want to do that, you want to take the derivative and set the derivative to 0 and determine if it's a maximum or a minimum. Okay? So that's what I'm going to do. I'm going to take this radial distribution function. This is it for the ground state of hydrogen. I'm going to calculate it. This is it. I'm going to take dr, so ddr of r squared and this exponential, this decaying exponential. I have to use the product rule again, because you can see there's two functions that depend on r. So I use the product rule for taking the derivative. You have to do that properly. You can do that. And if you do that, you find this. I've just taken the derivative of this function, and what I find is the following: bunch of prefactors, then something that says 2 minus 2zr over a, okay, and then r times this decaying exponential. This thing is 0, because I'm trying to find the maximum, okay? So when I set this to 0, I can see where, for which r, is this function 0. Well, there's basically 3 locations where it can be 0. First of all, there's a little r in there, so when little r equals 0, it's 0. But that's the nuclear position, okay? That's not it. Then, at infinity, because it's decaying exponential, it also goes to 0. But that's not really the most probable radius, that's just far away. So really, the most probable radius is this middle part, 2 minus 2z, z is 1, r over a. When that is 0, then I have the most probable radius. So that's actually not so hard, because it turns out that that location is simply a over z. Since z equals 1, z is the charge of the nucleus, the positive charge of the nucleus, I simply have this. This is the most probable radius. This a here, with all these prefactors that you didn't like last time in the lecture because you're like, ugh, too many letters, I don't like that. Turns out that A is actually the most probable radius to find the electron in the hydrogen atom. And look at this. This is very pretty. 4 pi, this is the vacuum permittivity again, h bar squared, reduced mass, and the electron. These are all natural constants. All of them. Nothing is assumed. There's no fitting parameters here. This is just, boom, a bunch of natural constants together give me actually a real number. Okay? The reduced mass is almost the same as the electron mass. Why? Because it is basically 1 over, reduced mass equals 1 over the mass of the proton plus 1 over mass of the electron. And since the proton mass is so large, that part doesn't really contribute because it's 1 over, very close to 0. So virtually, for our purposes, this mu is really just me, the mass of the electron. Okay? If you plug in the values, and all these values are known, because all of them are natural constants, you get this. It says the size of the hydrogen atom, or the most probable radius of finding the electron away from the nucleus, which is the definition of the size of an atom right here, is 529 angstrom, or 53 picometers. Okay? 53 picometers is the size of a hydrogen atom. Is it true? Is that really the size of the hydrogen atom? Turns out, yes, it is. It actually is. This theory predicts with a very high precision the actual size of the atom. Great win for us. Okay? This whole last couple of weeks actually was not in vain, because we actually have a real number here that can be verified, and it is true. You could never predict this with classical theory. It's impossible. You must use quantum mechanics. Okay? You must go through all this stuff to actually get these numbers out. And here it is. The size of the hydrogen atom comes out absolutely beautifully. It has a name. It's called the Bohr radius, after Niels Bohr. The Bohr radius is the size of the hydrogen atom, determined as its most probable radius, finding the electron away from the nucleus. All right. Now, there's also something called the mean radius. Remember, I have an operator for position, r, with a little hat. Actually, the hat should be there. Should be r hat, because it's an operator. Expectation value of that operator is what I would call the mean radius. What is the difference between the mean radius and the most probable radius? Well, statistically, that's very clear. If I have a distribution, and remember, we're dealing here with probability distributions, then let's say the top is the most probable place. Okay, if you do a measurement, that is the most likely scenario, the highest chance of finding an electron there. But you also have a chance of finding it somewhere else. It's just not as likely. The mean is taking the distribution and really determine the actual mean of the distribution, which is not the top. It's only the top that the distribution is perfectly symmetric. But if it has like a tail on one end, then it's actually more likely to be found on this side, okay, than on the other side. So the mean radius is a statistical notion which just determines the mean of, can I draw a line in this distribution that 1/2 is the same as the other half if you integrate it. This integrand here, this integral here is the same. That line doesn't have to fall exactly at the top of the distribution, okay? This is well known from statistics. The mean of a statistical distribution is not the same as the most probable location. This calculates the mean, so it's not the same as the most probable location. We calculate it in this way. We take the function, okay, there it is. R sandwiches between two wave functions. The wave functions are the same, okay, on both sides. So that's why I don't have the primes. The primes are not there. I just have one wave function. They're the same on the left as on the right. And I'm trying to kind of calculate this. The good news is that, again, this last section here on the right only depends on the angular coordinates, well, my operator only depends on r. Okay? That means this second part, again, is just a normalization condition for the spherical harmonic, which is 1, and I'm left with this integral. Okay? Just the operator r sandwiched between the radial wave function. There's a solution to this, which we don't have to go through, but I can give you the result. Here it is. The expectation value for the position operator is this. Okay? And it's kind of a nice result, because even though it has a bunch of things in it, you just plug in what L is, you plug in what N is, and you get an answer. Okay? So if my electron happens to be in a certain wave function with a certain N and a certain L, because that labels the wave function, I fill in these quantum numbers and I know what the mean radius is. Okay, now let's bring out some pictures of actual orbitals. And let's see what we can state about them based on what we just learned. Okay? So, s orbitals. You know s orbitals very well. But what is the definition of an s orbital in our framework? Very simple. The s orbital has L equals 0. That's it. That is the definition of an s orbital. When L equals 0, when you have a wave function where the L equals 0, that wave function represents an s orbital. If L equals 0, ML is always 0 as well. Okay? That's the s orbital. No matter what n is, n can be 1, 2, 3, 4, 5, doesn't matter. L, if L is 0, then you are dealing with an s orbital. So let's have a look at this guy. This is an s orbital because it has L equals 0. This wave function with the labels 1, 0, 0 is an s orbital. It's the 1s. It's the 1s orbital. The wave function for the 1s orbital. This is the one for 2s. I could just write it down. I have the tables, I have the polynomials, I have all these things. I can just write it out, what the mathematical expression for the 2s orbital is. Here it is. This is it for the hydrogen atom. It is an exact solution. It's an exact analytical expression. No approximations made here. Okay, so if I would plot now the probability map, again, I'm doing this with these dots. Okay, so think of every dot as a measurement, a hypothetical measurement. I cannot really do this measurement, but let's say if I could, it would look like this. For the 1s, I get this kind of like spherical distribution. For the 2s, also a spherical distribution, but there is a node within that distribution. You see that? 3s, again spherical, but now there's 2 nodes. 2 nodes along the radial coordinate. Note that any of these functions here do not depend on theta or phi. If you do not depend on theta and phi, then you are, doesn't matter which direction you point, you will be the same value. And that means that you are having spherical symmetry. All the s orbitals are spherically symmetric. They do not depend on theta or phi. They only depend on r. Okay? So, all of the s orbitals are spherical things, but they do differ along the radial coordinate. The 1s is the simplest, the 2s is also simple but has 1 node, the 3s has 1 more node, and so forth. Okay? This is another way to visualize it. Okay? All these representations basically is the wave function squared, represented in some sort of way, and we think of these things as orbitals. So if you ask me, or anybody on the street, what is an orbital, then the answer should be, it's the probability of finding the electron at the location close to the nucleus, which is described by the wave function squared, because that's a probability density. The wave function squared is the representation, the visual representation of the orbital. And this is just the plot of that. just plotting the wave function squared. This is the same information, but now represented in a different way. Again, I'm looking at the 1s, the 2s, and the 3s as a function now only of r. So I'm not trying to plot the whole thing in 3D. I'm just plotting it along r. Okay? So these things are spherically symmetric, remember? So it doesn't matter where I'm pointing, it looks the same anywhere. So I could just pick any direction and then trace out what is the probability of finding the electron along that radial coordinate. And I see these interesting distributions. Remember, this is the radial distribution function. Okay? It's little r squared times big R squared. That's what I'm plotting here. That's what I should be looking at. This is the 1s. That's the one we just looked at. The peak there is the Bohr radius. Okay? Over here. That is the Bohr radius. That's the size of the hydrogen atom. The 2s goes to 0 here. There's a node. And then peaks. The 3s is also a node very close by. Another node. 2 nodes. And then the peaks over here. So, if you look at this, you can see already that the 1s is the smallest, the 2s is second, and the 3s is the biggest, because the electron can be farther away from the nucleus on average, which means it has a larger size. If the electron sits in the 3s and not in the 1s, then the size of the hydrogen atom is bigger. Okay? The Bohr radius of the hydrogen atom is only the true representation of the size of the atom if the electron is in the ground state. If you put it in the excited state, the atom it's growing in size because the electron can be farther away on average. So the size of an atom actually depends on its excited state, which state the electron is in. Let's look at p orbitals. Everybody loves p orbitals. The p orbital definition is any wave function with L equals 1. Okay? That's the definition of the wave function that describes the p orbital. If L equals 1, I have 3 possibilities for ML. That means that for every L equals 1, there's 3 possible wave functions. They're not the same. They're all individual solutions, okay, in their own right. But there are 3 that are P, that have the label P. Independent of n. So I can have n equals 1, not n equals 1. N has to be 2 or higher. And a 3, 4, 5. I can have a 2p, I can have a 3p, I can have a 4p, and so forth. In all of these cases, there will be 3 2p orbitals, there will be 3 3p orbitals, and so forth, because of this relation between L and ML. So let's have a look at what these things look like. Again, I have now actual mathematical expressions for these puppies. I can actually write them out. This is L equals 1, ML equals 0, for n equals 1. Sorry, for n equals 2. Because when n equals 1, L can only be 0. So this is for n equals 1, L equals 1, and ML is 0. This is what the wave function looks like. If ML equals 1, then this is what it looks like. And if ML is the last possibility, is negative 1, then this is what it looks like. So there's 3 expressions. Each one represents an individual wave function. All of them are, in this case, 2p orbitals. One of them I call pz, and you'll see in a moment why. Then the second one is p plus, and the last one p minus. These are the raw solutions from the Schrödinger equation. And I want to point to the following. It actually has a complex exponent in it. See that? What does that mean? It means 2 things. 1, it's a complex function. It's not real because it has an imaginary part. 2, it depends on phi. And that means if I operate on it with my momentum operator, which is dependent on the first order derivative with respect to phi, I'm actually generating a constant, which will be my angular momentum. So these two guys, these two wave functions, represent a state in which the electron has angular momentum. Okay? All right, you may not be too excited about this, but it kind of like is not really a nice situation for me in terms of visualization. Okay, because that means some sort of angular swirling or something. Okay, so I don't like that because I want to see a shape that doesn't change over time. But I can do that because fortunately the energy of these two states are exactly the same, or all the three states are the same, and there's a beautiful kind of rule, I would say, you can easily prove that this is right, in quantum mechanics, that if I have two wave functions of exactly the same energy, I can make a linear combination of the two, which is an equally valid solution of the Schrodinger equation. It's very easy to prove this, but we'll just assume that it's right. And so why is that important for me? Because I will do the following thing. I will make a linear combination of this P minus and P plus. This is one combination where I subtract one from another. Okay, then I get this expression. And the second possibility is when I add them, okay, and I get this expression. Again, why would I do that? Well, this is allowed because I get, like I said, a linear combination of 2 or 3, 5, doesn't matter, functions that all are degenerate, make a linear combination. A linear combination is an equally valid solution of the Schrodinger equation. So why not do it if it kind of makes the expression easier to interpret? These expressions are easier to interpret. Why? Because you can see these are real and they don't depend on phi. That means they don't have angular momentum in this representation, and that means it's a standing wave. And standing waves is something I can easily visualize. Okay? So here they are, and this is what you of course find in textbooks. Okay? The PZ was already real. It is basically this distribution. It's this wonderful dumbbell structure, okay, that aligns along the z-axis. And then the px and py, which is defined on top, these are the actual expressions, look the same, but they align along either x or y. This is really cool because these are all standing waves, so I can easily interpret them. And I can see that the shape of all of these guys is the same. The only thing that changes is their orientation. Okay? Again, these are individual solutions of a Schrodinger equation. They are all valid. So they describe different situations. But because the shape is so similar, they all have one node, the same shape, their energy are also the same. So these all have the same energy. They're energetic. You can look at these wave functions and see, oh, wait a minute, there's some sort of relation between those. They have the same energy because they have the same kind of shape. Symmetry is an important part of quantum mechanics, which can get you pretty far in analyzing the results. Now, what is this representation here? These lobes, it's a very specific way of depicting orbitals. This is important. A lot of people, like yourselves perhaps, use these figures, or you're used to looking at them, and you don't know exactly what they are. These are the wave function squared, visualized at a particular point, namely the probability where the inside of this shape contains 90% of finding the electron. Okay? 10% out. So basically what I do, I take the wave function squared, I integrate up to the point where the probability hits 90%. The distance that I'm hitting it at for the integral is the distance that you see here away from the nucleus. So this is the 90% probability surface. That's what it is. These pictures represent the 90% probability surface, within which the whole thing is a 90% chance of finding the electron. But don't forget, there's a 10% chance of finding it outside, because orbitals don't have sharp edges. It's soft. It peters out. This is just a representation where we artificially make a hard edge at the 90% point. Okay? Don't forget. And also do not forget that the 90% chance of finding electron includes the whole thing, not just one side of the light. The whole thing, that's the whole wave function. The whole wave function is both lobes. Within both lobes together is 90%. All the space outside is 10% chance. Okay? Does it make sense? That's it. It's important to know that. Okay, one more, folks. D orbitals. I remember very well there was a student that was very excited about theoretical chemistry, and he had on his arms giant d orbitals tattooed. Okay, beautiful, beautiful tattoos. And 2 years into grad school, he wanted to be a theoretical chemist, he discovered that he hated chemistry after all, and he quit grad school and he went into banking. So somewhere on this planet there's a banker walking around with beautiful d orbital tattoos. True story. What is the definition of a d orbital? It's simple. It's L equals 2. Okay? Any wave function that has L equals 2 represents a d orbital. There's 5 possibilities because ML runs from -2 to +2 in integer steps. So for each N and L combination, I have 5 d orbitals. I have 5 d orbitals in the n equals 3. I have 5 d orbitals in n equals 4. I have 5 d orbitals for n equals 5, and so forth. Because of this rule. This rule, by the way, is not made up. It rolls out of the mathematics, and therefore, indeed, beautifully, this whole mathematical principle predicts the entire structure of the periodic table. Okay? As we will get into a little later. So let me just show you the d orbitals, the mathematical expression. You don't have to remember this, but I just wanted to show it to you, again, to reinforce the idea that all of these functions are now actual functions that we solved. They have an actual shape. We can actually plot them and actually see what the electron distribution is. Okay? So there's 5 of them. Here they are. You don't have to write them down. Okay? Well, you can, but it's easy to look them up. Here they are. As you can see, they look maybe a little bit more complicated. But this is what it is. You can see the R function is not, I didn't write out the R function. And I write it also in a particular way, namely in x and y coordinates. These d orbitals are, in a way, linear combinations as well, just like we did for the p orbitals. To construct the px and the py, we made linear combinations. These too are the result of some playing around and making combinations such that all of these represent standing waves. Okay, we do that because that helps us visualize what these orbitals look like. This is what they look like. You have seen them before, okay? And as you can see, very important, they have more structure than the p orbital. In fact, they have more angular nodes. Okay, instead of having 2 lobes, I have now kind of 4 lobes. I have, in all of these cases, I have now more angular nodes than I had in P. P only had 1, I have 2 here. This one too, by the way, maybe harder to see, but also has 2 angular nodes. If you have more nodes, that means you have more curvature, that means your kinetic energy must be higher to be in that wave function. Okay? Because anytime there's more curvature, there's more kinetic energy required to occupy that state, which means that these functions have higher energy than the P or the S. The S is lowest, the least curvature, P more curvature, this even more. Anytime you add more nodes, you must jack up the kinetic energy. There's no other way. Finally, this whole idea of nodes is important because it tells us a lot about the character of the wave function. There was a gentleman last lecture that asked about this, so I figured here it is. And I'd like to stress there's 2 types of nodes. Okay? Angular nodes. just looked at them. Okay? Basically, they depend on how you slice and dice the shape along the angular coordinates. But you can also, of course, have nodes along the radial coordinates. So there's two dimensions that we consider. There's nodes that the spherical harmonics have, and there's nodes that the capital R has, the radial part of the wave function. So we have radial nodes, and we have angular nodes. Okay? The number of angular nodes equals L. Okay, so when L goes up, I have more angular nodes. That's why the p orbitals, L equals 1, they have one angular node. The d orbitals, L equals 2, have two angular nodes. And maybe you can see that from the pictures already. F orbitals, 3 angular nodes. The number of nodes along the radial coordinate depends now on n and also on L. Okay? It's n minus L minus 1. That is the number of radial nodes. The number of times you hit 0 for the wave function along the radial coordinate. The total number of nodes is just the sum of these. And that happens to be n minus 1. Okay? N minus 1 is the total number of nodes. That basically means the number of nodes along the radial coordinate and also the angular nodes. Together do not depend on L. But please know what you're talking about. If you're talking about radial nodes or angular nodes or the total, it is a different expression, okay? So please specify what you're talking about. The radial, angular, or the total number of nodes of the wave function. All right, folks, that's all.